Hello, my name is Meg Carr, and I am a PhD student supervised by Chris Taggart at Dalhousie University and Angela Vanderland at Fisheries and Oceans Canada. Today, I'll present some of our preliminary work investigating fishing vessel risk to right whales in the Gulf of St. Lawrence. Vessel strikes are among the primary threats to survival for this critically endangered species. Mitigation strategies and available vessel strike studies primarily focus on large and faster-moving vessels, but Kelly et al. Found that even smaller and slower-moving vessels, such as 45-foot-long, 45-ton Cape Islander lobster boats, are capable of causing lethal injury to whales. These findings sparked our interest in vessel strike risk derived from smaller platforms, such as fishing vessels. Snow crab fishing areas are shown in the top right panel and are generally fished from ice out, which is when the Gulf becomes navigable and occurs around some point in April through mid-July. Visual right whale detections for the same time period are shown in the bottom right panel. Given the spatial and temporal overlap between snow crab fishing and right whales, we chose to focus on the southern Gulf of St. Lawrence. In 2017, 10-knot speed restrictions were implemented in the Gulf of St. Lawrence for larger vessels, over 20 meters. These restrictions are aimed at reducing the risk of lethality if a vessel strikes a right whale, since a fast-moving vessel is more likely to kill a whale upon impact than a slow-moving one. Large vessels have had to comply with speed restrictions since 2017, but fishing vessels above 13 meters and waters deeper than about 37 meters were first required to comply in 2021. To assess the lethality of potential strikes, we need to investigate the speeds at which fishing vessels are traveling and determine the lethality associated with these speeds. To map the probability of a fishing vessel striking a whale, we need to quantify the distribution of fishing vessels and whales in the Gulf. Once lethality and distribution are known, we can assess how fishing vessel risk varies across space and time, which will allow us to identify areas of concern with elevated risk. The overarching theme of this work is to quantify fishing vessel risk with the goal of informing more effective risk management in the future. We're using Vessel Monitoring System, or VMS data, for the Gulf of St. Lawrence in this study. VMS includes fishing vessel data, which are scrubbed, meaning vessel identities are removed and replaced by a unique identifier. This dataset consists of 356 to 432 unique vessels per year. It has full coverage of the snow crab fleet and partial coverage of additional fishing fleets. For each of the 3 years studied, there are over 1 million VMS observations, which are vessel positions with an associated speed. Additionally, the rate of observation for each vessel varied greatly. This may indicate that vessels targeting different fisheries are required to report their position and speed at different rates. Pictured in the lower right is an example of a snow crab vessel. This dataset is a bit messy. Firstly, the vessel speed observations are zero inflated. This happens because fishing vessels, in particular those involved in fixed line fishing, like lobstering or snow crab fishing, operate at 2 speeds: a fast transiting speed when they're steaming between locations, and a slow or nearly hove-to speed when they are actively fishing. Additional zero-knot speeds result from vessels reporting while they're at the dock, and those with faulty reporting equipment. The figure on the right is a histogram for vessel speed observations, where zero inflation is visible. Secondly, the rate of observations varies between vessels. This means that some vessels are overrepresented in the dataset, and others are underrepresented. A third problem we encountered is that some vessels don't report any information, possibly due to equipment failure. Now let's take a look at some data. The left figure shows a histogram for vessel speeds above 0 knots. You can see a bimodal distribution with many observations at low speeds and a second peak around 9 knots, which corresponds to the maximum speed of some fishing vessels. We chose to focus on speeds above 5 knots because these pose greater risk to large whales. This means we're focusing on risk while fishing vessels are transiting rather than actually fishing. Zeroing in on observations above 5 knots, I found that median speed ranged from 7.6 to 9.1 knots over the course of 2017. Next, we calculated vessel strike risk using 2 metrics, the first of which is the relative probability of encounter, which is the relative probability that a vessel strike will occur. This figure depicts how the relative probability of fishing vessel presence, seen in the left panel, is multiplied by the relative probability of whale presence, seen in the center panel, to find the relative probability of an encounter, which is shown in the right panel. This example was constructed using vessel data from 2017. You can see that the highest relative probability of a vessel strike occurs southeast of Miscou Island, which is circled in red in the right panel. The second risk metric we calculated, known as relative risk, combines both the relative probability of encounter and the probability of lethality. For this preliminary work, lethality was estimated using the Kelly et al. Shipstrike R package, as seen in the screenshot on the left. Our goal is to create a lethality curve for a ship with the dimensions of a typical Gulf of St. Lawrence snow crab vessel. To accomplish this, we need to estimate ship mass, impact height, and impact width. Currently, these metrics are not available, so for our preliminary analyses, we use a crab boat with a mass of 100 tons, which is roughly twice the mass of a Cape Islander lobster boat, and assume the vessel has a bulbous-shaped bow and strikes a whale at mid-body while traveling at 8 knots. This speed was selected because it's the maximum operational speed of many crab vessels. The figure in the lower right displays lethality probability over the duration of a strike. Time is on the x-axis in seconds, and lethality probability is on the y-axis. Lethality probability ranges from 0, where the whale has a 0% chance of dying after a strike, to 1, where a whale has a 100% chance of dying. The maximum lethality probability for this strike is 0.63, so there's a 63% chance that a whale struck under these conditions would die. Multiplying the relative probability of encounter by this value gives us a preliminary estimate of relative risk, which is seen on this slide. Relative risk for 2015, 2016, and 2017 are displayed in the left, center, and right panels, respectively. Here you can see that vessel patterns were very consistent among the 3 years. 2016 was the year with the highest total relative risk, highlighted in the center panel by a red circle. This was driven by vessel presence being concentrated across a wider area where whales were also concentrated when compared to the other 2 years. Though more crab pots were fished in 2017, fishing vessel traffic was constrained within a smaller area compared to 2016, resulting in the slightly lower total relative risk. Next steps for this project involve further investigating the typical dimensions of a snow crab vessel. Using these dimensions, we will quantify the lethality of a typical snow crab vessel across a wide range of speeds. We also plan to examine vessel speeds in greater detail, so lethality probabilities can be determined for each grid cell, allowing us to finalize our calculations for relative risk. After completing these steps, we will be able to map and quantify changes in lethal fishing vessel risk across the Gulf of St. Lawrence. Thank you to all the people and agencies that make this work possible. A special thank you to DFO for providing VMS data. If you have questions or comments about this work, please feel free to email me at meg.carr@dal.ca.